Welcome back to the channel. In the last video, we took a look at the stack category, and I did the valid parentheses problem, which is the only easy problem in the stack section. So we can cross that one off. And since this is the only easy one, I'm gonna head to the next category and see what's there. Overall, I've completed 5 of the 150 problems, slow but steady progress. And let's see if there's any easy ones here in the binary search category. I think I'll do that one next. Yeah, again, just one. I'm surprised actually how few of the easy problems there are. I figured there'd be far more. So, sorry I'm jumping around topics quite a bit, but to ease back into it, I am going to start out with all the easy ones. Okay, so let's get into the binary search. Let's see. So given an array of integers called nums, which is sorted, that's important. Sorted in ascending order and an integer target, write a function to search for target in nums. If target exists, return its index, otherwise return -1. Okay, you must write an algorithm with log n runtime. Let's see the examples here. It looks like in this array, if we search for 9, it should return that that is at index 4, because 0, 1, 2, 3, 4. Example 2. We search for 2, but that is not in the array, so we return -1. And then some constraints. Nothing. All the integers in nums are unique. Okay, and nums is sorted in ascending order. Amazing. So, like I pointed out above, this sorted in ascending order part, I think, is the key. So let me, as I always do, jump down to the whiteboard and let's talk through this. So it's been a long time since I've implemented a binary search. But what I remember about it is the list must be sorted. For this to be log n runtime. And we have that. So that's perfect, and that's why they've given us that constraint. So let's look at this first example here. Oops. And let me just talk through how the binary search algorithm works as far as I remember it. So -1, 0, 3, 5, 9, 12. Right, so with binary search, we basically want to divide the array in half every single iteration. And we can do that because we know that the array is sorted. So let me show you what I mean. So the first thing we want to do is we want to look at how long the array is. In this case, the length is 6. And we want to just go straight into the middle of that. So in this case, we would, to get to the middle of anything, we just divide it by 2. So that gives us 3. So the third element of the array is where we might want to start. In this case, that would be here with the 3. And so what we would do is say, okay, we're searching, remember, we're searching for the target, which is 9. So let me just write that. The target is 9. So we look and we check to see, is the element I'm currently looking at equal to the target? So is 3 equal to 9? It's not. So it's not this one. But now here's where the interesting part comes in and how this algorithm actually works. Because it's sorted, we know that our target 9 is bigger than the current value of 3. That's a key bit of info, because that means we know that we have to start searching to the right. We know that our target, if it's in the array, is somewhere to the right of the value we just looked at. So instantly, we can just ignore everything to the left of what we just checked. Hopefully that makes sense. So then, from here, we can basically pretend, so we know it's not either of these two. We know it's not this one because we just looked at it. So now it's as if we're considering a much smaller array, right? These are just these numbers here. Because we know it's not everything else because the array is sorted. And now we do the same thing. We take the length of this, it equals 3. We divide that by 2, that gives us 1.5. We can round that up to 2. And so we go to our second element in the array, which in this case is 9, and we check, does that equal our target? Remember, our target is 9, and it does. So we found it, and we can return the index, which in this case, we have to find some way to keep track of the index, right? Because I rewrote this array down here. But if we keep it all in the big array up here, we won't have a problem finding the index. So do you see how we were able to find the 9 by only checking 2 values? So let me just write that down. Checked 2 values to find the solution. We first checked the 3, then we moved to the right, and we checked the 9 and we found it. That's much faster than checking 1, 2, 3, 4, 5 values we would have had to check if we just looked through it normally. And that's how we get this O of log n runtime here. So hopefully that makes sense. Let's see if I can write the code that actually does that, because I understand how it works in theory, but I'm sure there'll be some edge cases I have to be concerned with here. So what to do first? I guess we need to find a middle point to start, right? So I'll call it middle. I'll set that equal to the length of nums divided by 2. So that'll give us the middle, well, let me call it middle index, just so I remember. The middle index is length of nums divided by 2. Great. Then what we can check is, and I know I'm going to need some sort of loop around this entire thing. So then we want to check this value, right? We want to check whatever is at middle index and see if it equals target. So if nums at middle index, if this equals the target, then we can return middle index, because we know that we found the target, and so we can return the index that it's at. Right. So if that doesn't happen, we know we need to adjust the middle index. Let me just write a comment for that. To search left or right. So basically, if target is greater than whatever the value was at that index, we need to search to the right. Otherwise, we need to search to the left. Just like the pictures I drew. So hopefully that makes sense. Now, I think what I need to do is keep track of a few other things. So I need to keep track of a start index, which I can set equal to 0, and an end index, which I can set equal to the length of nums. And the reason I have these is because I need a way to know when I have searched through everything, meaning if the element is not in the array, I need to know once I've considered everything possible. So I can set these equal to index 0 and then the length of nums -1, which is the highest possible end index I can search between. So this is between 0 and the length -1 is the entire array. And then as I go, I will adjust these. So basically I'll lower them over time so they get closer and closer together. And once they meet, if that's not the answer, then I know I have not found it. And you'll see that in action as I keep writing the code here. So now I can finally say while, I'm just going to say while true again here. I did this in one of my previous videos, and I know it's not the perfect way to do it, but I'm just going to loop forever and then exit when I either find it or don't find it. Right. I guess what I want to do here is instead of saying the length of nums divided by 2, I need to pay attention to what my start index and end index are at. So basically, I want to do end index minus start index end index minus start index divided by 2, right? Because say it's length 10 to start, I do 9 minus 0, which is 9. There are 9 elements. Divided by 2, 4.5, round up 5. That should work. And then this way it adjusts over time. Yeah, okay, I think that'll work. Great. So, and this also, importantly, if this gives me a decimal, it should just cast to an integer because end index minus start index will always be an integer, and then I'm dividing it by an integer. So this should round to an integer. I'm pretty sure that's how that'll work. I'll come back and double check it if something's not computing correctly. Okay, so then we check what that value is. If it's equal to the target, we just return the index that we are at. Now we need to adjust it. So if the target is bigger, I need to search to the right. So I can say start index equals middle index plus 1. This is a really important part. Does this make sense to everybody? What I'm saying is if the target is bigger than the number I look at, I need to search to the right of where I'm searching. So the way I can do that is the start index, which originally started at 0. I can move that up to whatever the middle index I'm at is plus 1. So I've essentially cut off the entire left-hand side of the array. And now I'll only be searching to the right of where I just looked. And the same thing down here. But we adjust the end index this time. The end index. So in this case, we have to search to the left. So the start index can stay the same, but the end index needs to equal the middle index, probably -1. Cool. So then, in what case do I return -1? I guess up here, if start index equals, or if start index is greater than end index, return -1. So what I'm thinking here is if eventually we keep moving the start index up and the end index down, eventually they're going to cross, and if they ever cross, we know we didn't find it. Let me give this a run and see what we get. And then let me move this over so you can see better. Okay, we got invalid syntax done. Oh, sorry. And I would like to move all of this up. I don't know why it changed the colors. That's kind of strange, but anyway, let's run that again. Time limit exceeded. So I must not be exiting the way that I want to. So let me add a check for equals there. Right, okay. So that's totally fine. Let's walk through this case one and see if I'm computing it correctly. So we end up putting the start index at 0, the end index at the length, which is 6 minus 1, so 5. So these are at 0 and 5. The start index is not greater than or equal to it, so then I calculate the middle index is 5 minus 0 divided by 2. So that'll be 2.5, which in Python, I think that just gets rounded to 2. So then middle index is 2. So the nums at middle index, that would give us this 3. That does not equal the target. So now we have to adjust things. I'm on line 19 here. And if target is greater than it, which it is, we want to change the start index to be the middle index, which remember was 2 plus 1. So the start index is now 3. And then we loop again and say, is 3 greater than or equal to 5? That's not true. So middle index is 5 minus 3, which is 2, divided by 2, which is 1. Oh, interesting. So now the middle index is 1. So, oh, I need to add these. I need to add them, not subtract them, because now 3 plus 5 is 8, divided by 2 is 4. Okay, that might have been the bug. Brilliant. So case 1 and 2 are solved. Let's give this a try. Submitting. Yes, all right. Glad we got that with just one simple bug. Looks like I have a middle of the pack runtime there. And I did really well in memory, so that's good. So thanks for watching. Got through another one without pinging Stack Overflow, so happy with that. And I'll be back next time. I guess this was the last easy problem in the, here, I can go back actually. So binary search, completed that one. And it looks like we're going to be moving into the sliding window. So thanks a lot, and we'll see you back soon.